So hello everybody. So today we are going to discuss about the thermodynamic classification of phase transitions. So in the last lecture we looked at Burger's classification of phase transitions. That is, phase transition can be of the reconstructive type and of the displacive type. We looked at it in the previous lecture, and we looked at this Burger's classification. As to reconstructive, we have the major reorganization of the crystal structure in terms of making and breaking of bonds, whereas in the displacive type we only have minor structural changes which involve distortion of the bonds, and there exists a definite structural relationship between the two phases. So today we are going to look into the thermodynamic classifications of phase transition. And in this regard, to start with, we are considering a compound, any compound which exists in the solid state has two polymorphs, 1 and 2. And we also need to consider the different thermodynamic quantities which are involved here. We are interested to look at entropy, we are interested to look at enthalpy, we are interested to look at volume and the Gibbs free energy. And when a phase transition takes place, we know that it is associated with a change in the enthalpy content, particularly if there is a phase change from polymorph 1 to polymorph 2, then we know that this process is associated with the enthalpy change, and the temperature at which this transition takes place is referred to as Tc, and the ratio of these two quantities tell us the entropy change associated with the polymorphic transformation. And we also know that every polymorph is associated with a Gibbs free energy which is represented as G1 and G2, and at equilibrium, that is at the point of phase transition, G1 is equal to G2, that is the free energy isobars, assuming that we are doing it at a particular temperature and pressure. In this case, the pressure is kept at 1 atmospheric pressure, so this is the free energy isobar. The delta G is equal to 0 at the point of phase transition of one form to the other. So because delta G is equal to 0, and from the expression delta G is equal to delta H minus T delta S, this is equal to 0. So delta H minus T delta S equal to 0, and this gives the relationship that delta H is equal to T delta S, from where we get the entropy change which is equal to delta H by T. And we can now look at the classification of the phase transitions. Phase transitions, to start with, are primarily classified as first order or second order phase transitions, which are the more popular ones, I will say. Even higher orders of phase transition greater than 2 are also possible, but we will not be looking at those. We will be focusing on the first order and second order phase transition, and we need to characterize these phase transitions from experiments and see how we can get an understanding of the variation in the thermodynamic parameters associated with first order or second order phase transition. So we start with the fundamental relationship which expresses the relationship between dg as minus s dt plus v dp, telling you that Gibbs free energy change are functions of temperature and pressure. So G is a function of temperature and pressure, and dou G by dou T at constant pressure gives us the entropy change. So this is expression number 1, and dou G by dou P at constant temperature gives us V, that is the volume is represented by the change in G as a function of pressure by the change of P at constant temperature. And we also have the other relationship, that is H is equal to U plus PV, where U is the internal energy of the system, H is the enthalpy, and P is the pressure, and V is the volume. And the first order phase transition essentially are characterized by changes in the first order phase transition is characterized by changes in entropy at the temperature of transition, that is Tc. They are also characterized by changes in unit cell volume at Tc, and this tells us that there are changes in the crystal structure between the two polymers 1 and 2. So it is not that that there is a gradual continuous change from structure 1 to structure 2, but effectively the crystal structure before the phase transition is very different from the structure after the phase transition, and it is also characterized by changes in density of the solid before and after the phase transition. So just to give you an example of first order transition, we can look at the crystal structure of cesium chloride and undergoes transformation to the rock salt structure. And here we see the temperature of phase transition is 479 degrees centigrade. The volume change in centimeter cube is 10.3, and enthalpy change is 2.424. In the case of we can take another example, for example of ammonium bromide, and we will come to this later, that what are the changes happening. We will see again in the case of ammonium bromide compound, we again look, it crystallizes in the cesium chloride structure, and its conversion into the rock salt type involves transition temperature of 179 degrees centigrade, volume change of 9.5 centimeter cube, and delta H of 3.678 kilojoule per mole. So the enthalpy changes associated with these processes is not very large, these are very small. Volume changes are finite, and the temperature of phase transition is also represented. So let us look at these quantities more carefully. So we have the Gibbs free energy as a function of temperature T, and this is representative for first polymorph, this is the representative for the second polymorph. So before the temperature Tc, so Tc is the temperature at which the G curves intersect. So G1 is equal to G2, and before the temperature Tc, the G1 value is lower than G2. So the polymorph 1 is the most stable phase. However, after Tc what happens? It is after Tc what happens? It is the G2 which is less than G1. So then G1 has got the greater value. So as if you take any particular temperature, say this particular temperature, you can see that this is G2 which is lower than G2, which is lower than G1. So this is 1 is stable. So after the phase transition temperature 2 is more stable, and we can also probe this by looking at the changes in G as a function of T at constant pressure, which is a measure of my entropy change, which is a measure of my entropy. So the entropy, the change in delta G versus delta T, this is more for the second polymorph compared to that of the first polymorph, and therefore there is a more rapid fall in it is a more rapid fall for polymorph 2 after the phase transition temperature compared to that for polymorph 1. So it is very clearly illustrated that after the phase transition temperature, the entropy of the higher temperature polymorph is greater compared to the first polymorph. Okay. Now that is because you are increasing the temperature of the system and you are forming a high temperature polymorph. Not only is the high temperature polymorph has got higher entropy, as is reflected in the more negative slope of del G by del T, we can also look at the corresponding H as a function of temperature, and here it is very clearly shown that at the temperature Tc there is a discontinuity in enthalpy, that is H1 is not equal to H2, and this much amount of heat has to be given to the system, and this much of enthalpy change takes place at a constant temperature, because the heat that is taken by the system now goes in bringing about the phase transformation. So there is a discontinuity in H at the phase transition temperature. So the enthalpy content of the higher temperature polymorph is also greater in comparison to the low temperature polymorph which exists before the transition temperature. So the high temperature polymorph not only has the high temperature, not only has higher heat content, but is also associated with higher entropy. And you can also look at the corresponding you can look also at the corresponding so that Tc so we can see that there is also a discontinuity discontinuity if you were to actually look at this, if you were to look at minus Ts1 as a function with respect to Ts2, there is also a discontinuity at Tc. So so we have both discontinuity in entropy So we have discontinuity in entropy, we have discontinuity in enthalpy, and these are characteristics of a first order phase transition, that you have these variations. So it is important to keep in mind now that at the phase transition temperature delta G is equal to 0, however delta H is equal to T delta S, which is not equal to 0, and this allows us to evaluate the entropy change associated with the process. So so just the first order phase transition we see very clearly is marked by a discontinuity in enthalpy, entropy. We saw the volume change. Also is changed. The structure is also changed. Now let us look at the second order phase transitions. The second order phase transitions are essentially characterized. These are characterized by discontinuities in the second derivatives of the free energy. in the second derivatives of the free energy. So we are now looking at the second derivative. So we are now going to look at these quantities, that is del square g by del p square. So we had looked, so we now look at the second derivative of this quantity. So del square g by del p square, and this is equal to dou v by dou p, which is actually minus v into beta, and beta is called the compressibility of the substance. We can also look at del square g by del t del p, which is equal to del v by del t, because that is the second derivative we are taking with respect to temperature, and this is v alpha, where alpha is the thermal expansion of the material, thermal expansion coefficient. Beta is the compressibility factor, and we can now take del square g by del t square, which is minus del s by del t, and at the phase transition temperature this is equal to minus Cp by T, and Cp is the specific heat capacity of the substance. So these are the three very important relationships, that is the second derivative of G with respect to P, the second derivative of G with respect to now T and P, and the second derivative of G with respect to T. And these tell you that there are discontinuities now in the compressibility factor, thermal expansion, and the specific heat capacity, and these are characteristic of the second order phase transition. That means that the quantities which reflect the first derivative, that is for example the entropy changes, we have got the entropy changes, and we have also got the enthalpy change. So we have got the quantities H and S. So H and S are continuous at Tc for second order phase transition. So we are able to determine a first order phase transition by looking at a discontinuity in H and S. However, for a second order phase transition, these quantities H and S are continuous at the Tc for a second order phase transition. So how do we represent these continuous changes which happen in the structure till you reach Tc, and what happens after Tc? And this in order to understand the representation of the second order phase transitions and the variation of the thermodynamic quantities with respect to temperature, we can now plot, to start with, G versus T, and so this is polymorph 2 and this is polymorph 1. This is the undercooled this is the supercooled 2. This is the supercooled phase 2. So, and this is the temperature Tc, where you can see that there is no discontinuity in the process, but there is a gradual increase in you can see that there is a gradual that as the temperature gradually increases. So this is the temperature axis T, there is a change, continuous change happening, there is a continuous change happening from 1, and after Tc it has completely converted into the phase 2. So now the interesting thing is that when you can actually go below the, you can actually go low in temperature and can still supercool T, you can still supercool the phase 2, but you cannot superheat, you cannot go here, this is not allowed. Why? Because the process of conversion of 1 to 2 has already started from 0 Kelvin. So, in principle, say even if you are at room temperature and then you start heating the substance, by the time you reach Tc, the phase transition had already started from 0 Kelvin and continues in an increasing rate, because we also need to keep in mind that the thermodynamics is an important factor here, but the rate also is already integrated to the system. So, there is also a rate associated with the transformation process. So, we are assuming that this transformation is happening slowly as a function of temperature, and by the time you reach Tc, the phase transition which had already started starting from 0 Kelvin, and now we are at room temperature, and it continues at an increasing rate with increasing temperature, such that when Tc is reached, the phase transition is complete. And now when you go across the phase transition temperature, there is no reason for a discontinuity in the value of the entropy change. There is no reason for a discontinuity in the entropy change or the enthalpy change, because the process has been happening in a continuous manner, and essentially this tells you that when you reach Tc, the conversion from 1 to 2 is already complete. So, there is no reason why you should be able to superheat 1, because 1 had already completed its complete conversion into 2. So, it is not possible to superheat 1, but it is definitely possible to supercool 2 and progress along the dashed line if given an opportunity to do so. So, you can actually supercool 2 gradually, but you can prevent its conversion to 1, but you cannot superheat 1, because 1 has already completed converted into 2. Now, in order to understand this picture more carefully as to what is happening at the structural level, these kind of transitions are also referred to as order disorder phase transitions, and this can be easily understood if you consider, for example, AB solid, in which at 0 Kelvin the positions of A and B are well defined. But if you now start increasing the temperature, then A and B start randomly distributed. They start randomly getting redistributed at different sites. So, at 0 Kelvin, the crystal structure was characterized by long range ordering, which we call as LRO, and by the time we have almost reached to the transition temperature, that is Tc, there has been an extensive redistribution of A and B at different sites, and this increase in the randomness essentially contributes to the disorder of the crystal structure. That is, by the time you have reached Tc, and if you go even beyond Tc to higher temperatures, there is now a random arrangement of A and B, such that statistically A would like to be surrounded by B and vice versa, and therefore this referred to as short range ordering. This is referred to as short range ordering. So, at Tc, the long range ordering has been completely removed, and it is only the short range ordering which exists at Tc. That means the structural changes have already started with the increase in temperature, and this is referred to as order disorder phase transition, and this allows us to understand the gradual changes which are taking place in G as a function of temperature, particularly when we go across the phase transition. So, this process can also be quantified as the long range ordering as a function of temperature, where we see that the phase 1 is converting gradually into phase 2, and when you reach the temperature, when you reach this particular temperature Tc here, it is completely converted into the phase 2. So, the long range ordering goes to 0, it is the short range ordering which exists at Tc, and these are this essentially is a signature of second order phase transition, which are of the order disorder type. And it is also now important to look at the corresponding enthalpy changes which takes place, because we know that there cannot be a discontinuity, because discontinuity where H1 is not equal to H2 is a characteristic of first order phase transition. So, we now look at H as a function of temperature, and so there is a so you see here, this is the Tc. At Tc, H1 is equal to H2, and this is not exactly a first order phase transition, because at first order phase transition we saw that H1 is not equal to H2, and it indicates that there is that very close to the transition temperature Tc, there is a substantial anomalous increase in enthalpy. The enthalpy value or the H component increases at close to the Tc. There is an anomalous increase in H. So, it is not discontinuous, it increases from H1 to H2, and it increases gradually, but it is anomalous in the sense that we are not able to account for its origin. But so then we need to now recategorize our concept of phase transition, because we need to understand, in one side we have a discontinuity, in the other side we have got a continuity of the thermodynamic parameters, and it is at this time that the scientist who came into the picture was Ubbelohde, who defined phase transitions as continuous or discontinuous in nature. Who defined phase transitions as being continuous or discontinuous in nature. And one thing I must also mention here, that when you have this kind of a response in the H versus T plot, what you can now plot is Cp versus T, and there we as we had showed you that if you plot Cp versus T, it goes, there is a discontinuity in Cp, there is a discontinuity in Cp at Tc. So, you can now plot the specific heat capacity as a function of temperature, and you can see the discontinuity in there is a discontinuity in Cp at Tc, and this is a finite discontinuity in Cp at Tc, and that characterizes the second order phase transition. So, what Ubbelohde had said is that when you have a first order phase transition, then definitely it is discontinuous, but for a second order phase transition there is a gradual smooth change and a continuous change in the structure of one polymorph to the other, and this process is already taking place before you have reached Tc, and these kind of changes which were happening, the changes happening before Tc is reached are called premonitory changes. These are called premonitory changes. and the premonitory changes which take place because of the gradual and continuous change in the crystal structure cannot be ignored. So, the premonitory changes are very important, and these happen for the thermodynamic parameters, happen for the thermodynamic parameters, that is for S, for H, and they are of more of a continuous kind, and these premonitory changes are already happening below Tc, and after Tc there is again a continuous change in S and H, indicating that the second order phase transition has already been completed. Okay, has already been completed. That means technically for second order phase transition, we know that H1 is equal to H2, that means delta H is equal to 0. But in reality, when you will actually map the second order phase transition using, for example, DSE, you will see that there is a minor drift from the baseline, indicating that no matter whatever the order of the phase transition, as long as there is a structural change, even of a very subtle kind, it will always have the character of first order in it. So, you cannot have a pure second order phase transition or a pure first order phase transition. These are ideal things. First order is still very well understood and characterized, but second order is something where you need to look at the changes in the thermodynamic quantities in a more careful, because these can also involve subtle changes, and you cannot ignore a first order phase transition, the character of first order phase transition, and also second order phase transition as well. On the same line, if you were to actually look at Cp versus T for a second order phase transition, it has got an infinite, it is discontinuous. Sorry. So, you see it has got it becomes infinite at t equal to Tc. So, it is characterized by an infinite discontinuity at t equal to Tc, and the driving force for the order disorder phase transition, which I would like to mention, is the entropy change which takes place at the phase transition, which is characterized as R ln omega 2 by omega 1, where omega 2 is the number of independent orientations at high temperature. W1 is this number at low temperature. So, it is kind of a contribution towards the statistical entropy, and in this regard the entropy changes are primarily you can have configurational entropy, vibrational entropy, rotational entropy, but here it is the configurational entropy which contributes and drives the phase transition processes. And we can look at this order disorder phase transition with respect to one particular example I would like to mention, that is we can look at the cesium, we can look at ammonium bromide as I mentioned to you, and we can look at the bromide structure. We can look at the bromide structure, the structure of ammonium bromide. And we have the ammonium ion sitting here, and these are hydrogen bonded here with the two bromines, and then here with these two bromines. So, there is one set of ammonium here which involves hydrogen bonding with these two bromines, but in the other one we have the other 4 bromines involved in hydrogen bond, that is these ones now. Okay, so you can see in one case you have got this these and this. I would like to know about this one, and in the other one you have got these and these. So you have two different orientations of ammonium ion. Now in the ordered phase, you have the ammonium ions in only one particular orientation in all the unit cells, but in the disordered phase you will have the ammonium ions in either disorientation or disorientation, and this is statistically distributed randomly in different unit cells. So the number of configurations is only 1 for the ordered phase, but the number of configurations is 2, and that tells you that delta S is equal to ln R ln 2, and this is the magnitude which drives favorably the process of phase transition, because there is a increase in entropy associated with this process, thereby validating the ordered disordered phase. So these subtle changes in the entropy can actually guide these phase transition processes as well. So I hope with this discussion we have been able to appreciate the nature of phase transitions, first order and second order. And now, keeping these things in mind, we will now in the next lecture look at how these phase transitions take place with different conditions. These conditions can be chemical in origin, they can be electrical in origin, and we can look at temperature, pressure, different factors, different kind of stimuli, light for example, or we can change the pH, we can apply mechanical stimuli, we can apply we can apply stress or different kinds of stresses, and we can change we can put in different chemicals in which the structure can respond and change from one structure to another. So all these stimuli can lead to phase transition processes, and we will discuss more about this in the coming lectures. Thank you.